All right, so today I will talk about my project, which is imaging of 3D objects with experimental data using orthogonality sampling methods. And this is joint work with my advisor, Liam, an undergraduate student, Hayden Smith, and Rome. Let's get started. So in this talk, first I will briefly introduce about electromagnetic inverse scattering problem and sampling methods. Then I'll talk about the modified version of orthogonality sampling method for non-magnetic and magnetic cases. And finally, I will show some experimental results. So you can see here in this simple model, we send some electromagnetic wave or incident field E in toward an object, let's say omega. Then we can have some scattered field denoted by U. So there are two types of problems, direct and inverse, right? And the direct problem, given incident field and the object, we try to measure the scattered field. Inverse problem, in another hand, we know incident field, we can measure the scattered field, and we will try to determine omega. And in here, we try to reconstruct location and shape of omega. So that is the electromagnetic inverse scattering problem that we are working on. Okay, some applications of this problem. So first, in non-destructive testing, they can use it to evaluate some properties of a material without destroying the whole system or causing any damage. Or in medical imaging, they can use some, something like X-ray, CT scans to provide images of inside of a body for clinical analysis or medical intervention. So yes, breast cancer, they can study that using inverse problems. And another application here, radar, inverse problem can be used to detect aircraft, spacecraft, ship, motor vehicles, or weather formation. And they also use it to study geophysical exploration to explore the subsurface of the Earth. And the model, the problem that we working on here, it is more applicable, it is more focused on non-destructive testing and geophysical exploration. Okay, so the electromagnetic waves can be described, the behavior of it can be described by Maxwell's equation, which is given in the formula number 1, as you can see. So here, E is the electric field, H is the magnetic field, K is the wave number. And the target omega here, we consider it, we assume that it is an isotopic medium. So it is characterized by two parameters, mu and epsilon. They are matrix value functions from R3 to C3/3. And in fact, they are magnetic permeability and the electric permittivity of the target of the medium omega, respectively. So the Maxwell system number 1 here, we will rewrite it as equation number 2, where we eliminated the magnetic field H and just left over with the electric field E. So we obtain the second order for E, right? And number 3, it tells us that the total field E satisfies, it is the sum of the scattered field and the incident field. And number 4, it is the radiation condition. So to sum up, the inverse problem that we want to solve, given the far field measurement of the scattered field U that satisfies equation 2 to 4, we will try to reconstruct omega.
Very good introduction. So
yeah,
very good. Yeah.
Yeah, so in here we will try to reconstruct location and shape of omega. So the difference of this inverse problem compared to Trung's work is that the target here, it is bounded, and it's not periodic. So it's just like some bounded target, non-periodic. Okay, so in order to solve that inverse problem, we're gonna use sampling methods. So the idea of sampling method is that first we're gonna discretize the domain into many pieces like that, and we will have a sampling point, let's say ys, and it is associated with a criterion, which is a functional I of ys. And the value of this functional will indicate whether or not the sampling point ys is inside or outside of the scatterer. Yeah, so that's just the simple principle of the sampling method. So this method has been studied in the past 2 decades, and I list here some books on classical sampling methods. So in 2008, Kish and Ginbert, they published the book Factorization Method. In 2011, Kalkony, Contant, and Monk, they published the book for linear sampling method. And for recent study for sampling methods, so in here we have orthogonality sampling method, and so people study it for scalar Helmholtz equation and Maxwell equations. Scalar Helmholtz equation, it is associated with the acoustic wave, and Maxwell equation, we know that it is for electromagnetic wave. And here I list a non-complete
So
list.
Helmholtz equation is for like detecting the sphere shaped objects like the heart, the lung, you know?
Yeah.
So
right.
it's like, so you give 2 equations, right? So the Helmholtz equation is associated with the rounded objects or the like a flat or tubed object like the instance, you know?
Sorry, I'm not quite get the question, but like the equation that we consider here, it is Maxwell's equations.
Yeah.
And it describes the behavior of electromagnetic waves.
But you didn't give the Helmholtz equation, right? Do you?
Yeah, the Helmholtz equation.
The Helmholtz equation.
Homogeneous.
No. The third slide.
Okay. Third.
No. The equation, the 2 equations you took.
Yeah. Is that number 3 here?
So this equation is the Maxwell equation, right?
Yeah. So just to clarify, the Helmholtz equation, it is for acoustic wave, and the Maxwell's equation for electromagnetic wave.
I see. Okay. So the question I have is whether Helmholtz equation is used to detect the round objects.
The round object?
Round like hearts is round, right? Like the lung is kind of round, you know? Like the head is also round.
Yeah. Right.
Yeah, I mean, we have instance in our stomach. So that's long, right? That's like tube, you know? So I was wondering whether the Helmholtz equation is for rounded objects, you know?
Yeah, both of them can be used for round objects. It's just different in the incident wave that you send toward the objects.
I see. Okay, good. Yeah, continue, please.
Yeah, great questions. So here, yeah, so I list a list about some literature about the orthogonality sampling method. Um, and then in this talk, we want to investigate the modified orthogonality sampling method. And we study it for Maxwell equations in non-magnetic and magnetic anisotropic media. So let's compare a little bit between the OSM, the orthogonality sampling method, with classical sampling method. So we see that first, it is simpler to implement because we don't have to regularize the impulse inverse problem. And second, it is stable with respect to noisy data, and it's versatile, so we can either use one wave or multi-static data. Uh, and compare the modified version with the original version of OSM, we see that the modified version, it is more applicable to different types of polarization vectors associated with the data. Okay, so let's go back to the problem setup. We consider the incident plane wave that satisfy that formula. And in here, we denote S squared is the unit sphere. So you see in the formula of incident plane wave, we have D is the direction of the incident propagation. Q is the polarization, which is orthogonal to the direction D. Okay. Now we realize we have a property that the scattered field U satisfies formula 5. So this basically tells us that if you measure the scattered field far away, so you let the modulus of x tends to infinity, then you can rewrite it in the term of the far field part and U infinity, where you measure it, x hat and d here belong to the unit sphere, okay? So we rewrite the inverse problem, we restate it. So given the data is the far field pattern U infinity, where you measure for all x hat and d on the unit sphere. With a fixed wave number k, then we'll try to determine the unknown target omega. So now move on to the next part. We consider the modified OSM, and we consider for the non-magnetic case where we have the magnetic permeability, mu is equal to the identity matrix in R3. So first, we have a look at the factorization analysis. We introduce the far field operator F, which is the integral of the far field pattern. Then we define the solution operator G that turns the incident waves into the far field pattern. And then we define the Herclotz operator H. So this basically kind of like the integral of incident waves, the sum of incident waves. And then we obtain the first factorization. It says that F is equal to G times H. Next, we introduce the middle operator T, like that, what P is the epsilon mu minus the identity matrix, and we obtain the second factorization for the far field operator F. So we can rewrite F as H star T times H, and you see the operator T is in the middle, so that's why we call it the middle operator. Then we come up with this lemma here, proposed in 2014 by Haddad. So if we assume that the imaginary part of P is uniformly positively defined, or there's a constant, non-negative constant, such that the real part plus gamma times the imaginary part is uniformly positively defined. And if the imaginary part of P is positive semi-defined, P is defined like that, okay? Then we can show that the middle operator is coercive. So a bunch of conditions for the parameter epsilon, and then we can show the coercivity of the middle operator. So combine the factorization here and the coercivity of T, we then can prove that the inner product of F is bounded below by the norm square of the Herclotz operator H. Okay, now we can talk about the imaging functional of the modified OSM. And before we do that, let's recall the original imaging functional. That was studied by Harris and Wynn in 2020. So this is the formula of the original OSM. So you see, with a given sampling point, right, you will have the input data is the far field pattern here that you can measure around the target. So you plug it in here in that double integral, you'll be able to evaluate it, and then you will have like some values of this imaging functional, and it will tell you whether or not there will be some criterion that we will talk about that later, but the value of this imaging functional will tell you if the sampling point is inside or outside of the target. Then you can reconstruct the target. So that's basically the main idea. However, to evaluate this integral, it requires that the far field pattern, the data, the polarization of U infinity, it has to have that particular form, D cross P cross D. Okay, so there's some restriction on this. Now we want to extend that. So we define the imaging functional for the modified OSM, where we say that, well, now the polarization, it can be the linear combination of D cross P cross D and D cross B, where alpha 1 and alpha 2, they are some numbers. So this new imaging functional can be applied for more different types of polars. The most general formula of the polarization is that when you have alpha 1 and alpha 2, they are functions of D. But that case is very complicated. So here, well, at least we can have more relaxation on the polarization, where we have alpha 1 and alpha 2, they are some numbers. And also we interchange the role of X hat and D in the old imaging functional. Anyway, so this is the new formula, the modified version of OSM. And then we obtain the lemma. We can rewrite this imaging functional in the term of the far field pattern. So this lemma is very nice because we can access to the far field operator of the data directly. Okay, now this is the main theorem of this project. So we can have an estimation for the imaging functional. So you can see here, we can derive the upper bound and the lower bound for the IMOSM. And these bounds, they are written in the term of WYS and VYS, okay? And the formula of WYS and VYS are given in the following here. So they are just like cosine, sine function, modulus of Z. They are function in R3. And so that we can.
So the results basically says that if the point is not in omega, then that's well controlled. Then if it's in omega, it's non-trivial. So you can always detect something.
Right, exactly. Yes.
Okay.
I will say it more clearly in just next couple of minutes. So we remark here, very, very good point, thank you. So we remark here the function of W and V, they pick their modulus square, pick when the modulus of Z is small, and they will decay rapidly when modulus of Z is getting bigger. So because of that property, then we can realize the behavior of the imaging functional, right? So we see that the imaging functional will have large values if the sampling point is inside the target, and the imaging functional will have significantly small value if the sampling point is outside the target. So, and also we can show that it decays as the big O distance between the sampling point and the target to the -2 here as the distance tends to infinity. So this is the indicator for us to reconstruct the the target omega. We only have to like evaluate this imaging functional, and this imaging functional basically it's just the double integral, so the computation cost for it is very cheap. Okay, so here I give an illustration for modulus of omega v and norm square of h. So our real target is the or omega, it is the ball centered at 0 with radius 0.5, and you can see here omega and v, they pick inside the target and they decay rapidly outside of the target. Okay, all right. So I sketch a little proof here. So basically we use the factorization for f and the coercivity of t, and then we can derive the upper bound and lower bounds for the imaging functional in the term of norm square of h. And h, it is the linear combination of w and v, and we can show that w and v, they are orthogonal, so that we can apply the Pythagorean formula here. And then we use the von Haeckel formula to evaluate the norm of w, sorry, to evaluate w and v, so that we can have sine, cosine function, the formula that I showed before. Okay, then we also can show that this method is stable. So we assume that if the data that we have, it is noisy up to this perturbation, then the error in the imaging functional is bounded above by that quantity. Okay. And next, modified OSM, we study it for the magnetic case, where you have here mu, it can be any arbitrary matrix value function, not just an identity matrix. So the idea pretty much the same. We define Five-field operator, solution operator, obtain factorization for f, and the second factorization, and then we also can prove that the imaging functional, the imaginary of the middle operator is coercive, and we obtain the same result here, the same behavior for the imaging functional, and we also can show the stability estimate. Now let's move on to the last part, my favorite part. We talk about experimental results. So here we're gonna test the method against real data. So we use real data provided by Fresnel Institute in French, and you can see the setup that I have here is kind of fancy. So we have a semicircle with two antennas, they are movable. The two antennas here, they will send incident wave toward the object, and you can see the object is very tiny. It is on the top of the pencil, and the pencil, it can spin around its center. And we have another antenna on the right corner, and this antenna here is fixed, okay, and it will measure the scattered field. Okay, all right, so what we are given only the third component of the far-field pattern unity. In theory, we assume this guy is a vector in R3, but now we only know the third component of it. And the source, we have 81 points distributed evenly on the unit sphere, and we have 36 points receiver only on the disk. So you can see that the real data, it is very limited in that sense, right? Third component for pattern and only 36 points on a disk, where in the theory we assume that we know X hat all over the unit sphere. Also, we scale the data, we set 40 millimeter to be 1 unit of length, and we invert the calibrated co-polarized data sets. So yeah, we use that data sets. So here they are 5 exact scatterers that we tested, 2 spheres, cylinder, two cube spheres, and iso-k-spheres. So this is the first case, two spheres. So you can see the exact scatterer at the beginning, and then FM, it is a classical sampling method. It is called factorization method. So you can see this classical sampling method, it gives a reasonable reconstruction for the location of the true object. However, it cannot reconstruct the shape of the exact scatterer. Well, that because the real data, there is some sort of noise in the data, and classical sampling method, they cannot handle noise very well. Okay, the next result here given by the original orthogonality sampling method. And well, if you project the reconstruction here on the XY plane, you see that, well, the projection is kind of close to the true image. However, it failed to reconstruct along the Z direction. And we try to explain that because we only have 36 points receiver on the disk. On the disk. So the data is very limited. So that is why it cannot reconstruct shape or location of the true object very well for the original OSM. Now, the modified version that we study, luckily, it gives reasonable result for both reconstruction and location. It gives reasonable reconstruction for the shape and the location of the true object. And the last two pictures, they are cross-sectional picture of the reconstruction. Okay, for the cylinder object, again, FM failed to reconstruct shape, but can reconstruct location. OSM failed to reconstruct along the Z direction. Modified OSM still give reasonable result for both location and shape. The exact scatterer for the two cubes case here, FM give pretty good results. OSM again failed to reconstruct along the Z direction. Modified OSM still doing well. In the cross-sectional picture, you can see they give precise location, right? Cube spheres, and the last case, iso-k-spheres. So in this case, FM give us nothing valuable, but MOSM still gives good results. Yeah, so that pretty much it. And thank you so much for listening to me.